Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In this video, simply we are going to learn about another classification algorithm, Naive Bayesian. In short, Naive Bayesian is a very simple classification algorithm that uses the statistical and probability paradigms in going about classification. And in this video, we are going to see what that means and how that looks like, and also we're going to see how we can do this in R. Let's look at this slide. Alright, so during these slides we're going to learn about Naive Bayesian or Naive Bayes method using example and see how it uses probability in the basically going about classification, and then we'll see another example and we'll do the Naive Bayesian classification in R. So it's just going to be a very simple video as far as how it looks like, just what it is, and then we'll wrap things up with a summary. Alright, so just to recap, we've got classification, like we are going to use Naive Bayesian for classification, and classification is for figuring out a class or a label of a data object based on its property. For us to be able to do that, what we do, we connect independent attributes or the properties to the dependent attribute, right? So this was what we try to do in classification, and classification is when this is categorical, right? So that's what we are trying to do. We are going to see how Naive Bayesian goes about finding these relationships, and so it can use those relationships to predict the categorical class option label. Naive Bayesian and KNN are kind of similar in a sense that, as we talked about, KNN is a lazy algorithm, remember? We haven't seen an eager algorithm yet to sort of see what that means, but what that means here is that when we have a classification task, when we want to use KNN or Naive Bayesian, there is no process of going and finding relationships and creating a model, right? We don't create a model and then come back to be able to predict these new values, right? With Naive Bayesian and KNN, what we do, we say, okay, we've got this data, we know the labels for this data, we have a data, we don't know their label, right? We don't know this label. And this example is going to be if we are going to accept to give loan to a few customers, what is the customer income, what is their years in current job and their education level, and based on these three attributes we want to see if we want going to give loan, or we're going to see if the customer are going to pay their loan in full or not, right? So this is a class label in this example, and this is what we are trying to do here. These are independent attributes, these are predictors, and this is our target or our dependent attribute, right? So here our data set has labels for targets, but for our new data set, which we are interested to know if we should accept loan or not, or if these customers are going to pay the loan in full, we're going to basically use the knowledge we can get from this data and use that to come to a decision about these data. So that's what we are trying to do here. And KNN and Naive Bayesian don't spend time sort of creating something to learn, and then after they learn and then they use those patterns and the sort of structure that they have to come to this prediction. KNN and Naive Bayesian, whenever they come in new data, they say, okay, now let me go through the data, and based on what you are telling me, let me go and see what the data tells me. So basically, they grab that case or data object and say, okay, let us go through the data and see what we have, and then they come back with an answer. Once we talk about lazy algorithms, which is going to be the next algorithm, decision tree that we will see, which is a Naive algorithm, you will make this conversation will make much more sense to you. All right. So here we want to make that decision for this one data set, and we go back and come to yes or no. One thing we need to pay attention to is that Naive Bayesian has a specific requirement for the data. The data has to be in categorical way. So it's going to be, if we have numerical attributes the way we do have here, we've got two numerical attributes, we have to sort of like approach it from two possible perspectives. We can do discretization, or we can sort of like assume a probability distribution for the numerical attributes. We will see both of those and how those can be done. But let's go with the discretization first. So we'll look at the discretization. For this example, what that means, discretization is we've got numbers here, we turn them into categories. And we have used a very simple discretization rule. If the value is smaller than mean, and use low, otherwise high, right? The same thing for this one. So we discretize the data. Now we're going to use this data. Now we're going to use this data for Naive Bayesian, right? So now this is our data, and this is what we are trying to do. We are trying to grab this one new data and you go through this. So actually, this is going to be Naive Bayesian. Go through this data and come back with an answer, yes or no, right? So that's what we're trying to do. So what does Naive Bayesian do? Naive Bayesian uses a posterior probability, and that's what that means. Posterior probability is a conditional type of probability that we say the probability of having a yes, which means customer will pay the loan in full, given a specific customer, or given a set of independent attributes, possibilities, right? So this is what we have here. We've got, what is the probability of yes if A1, which is attribute 1, which is applicant income, is high, right? So this comes from here, and if the A2, which is years in the current job, is low, and A3 is education level if it's masters, right? So basically we are saying the probability of yes given this customer, right? We know this is the customer, but here we are making a very big assumption. We're assuming that when we have applicant income high, years income, job, current job, and master's level, we're assuming that these attributes, the fact that we've got education level is master's, and the income is high, they are not independent. They're independent. They're not dependent to one another, which is we know is not correct. So we are making an assumption here, and that's why we call Naive Bayesian. We'll talk about that a little bit further down this video. But anyway, let's move on. And here, for sake of simplicity, we say P probability of yes given xy. Probability of yes given this is the customer, or these are the possible values for the independent attribute. So that's what we're going to do. So what we are going to use is going to be the Bayes theorem. We've got the conditional probability formula, which is probability of A given B is equal to probability of intersect A and B divided by the probability of B. And you can, use this formula, which is the conditional probability, to prove this one. Here we're going to use this formula basically. We're assuming that this is correct, and we're going to use it for finding the class of the state object. So now we have to sort of like write that in our terms. So we've got probability of yes given x1, right? If we use Bayes theorem, it's going to be, I'm just going to use, rewriting that based on this being a yes and this being x1, right? So probability of yes given x1 is equal to probability of x1 given yes multiplied by probability of yes divided by probability of x1. So now we're going to go one by one to these elements and calculate these three values. Once we do that, then we can come to a probability value. That's what we're going to do here, right? So let's start with probability of x1 given yes, right? So if we want to calculate this probability value with our assumption that these are independent, we can sort of say probability of x1 given yes is equal to probability of customer is equal to high given multiply. Remember, we assume that these independent attributes are independent, and because of that we can multiply them. And then we've got probability of years in current job given yes, and multiply probability of education level, right? So we've got three terms we want to calculate here, right? And to be able to calculate that, because this is all of them are conditional probability yes, we only have to pay attention to the parts of the data that have yes. So these are the only part that we want to pay attention. So right, so these are the ones that are yes because it's all of them are given yes, given they have paid in full, right? So these are the only parts of the data that we want to look at, right? So let me go ahead and sort of so now we can calculate this one, probability of customer income being high, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 cases. So we've got 9. And how many of them are high customer income? 1, 2, 3, 4, 5. 5 of them are high. So 5. So this was this part. Okay, let me use some color here. So this was this. Now I want to calculate this. Okay, I want to calculate this. So now it's going to be years in current job low. So it's going to be 1, 2, 3, 4. So it's going to be 4. Let me see. 1, 2, 3, 4, 5 actually. It's going to be 5 divided by 9. 5 divided by 9. And let me put another. And I'm going to calculate this divided by again 9 because we've got 9 yeses, and masters 1, 2, 3, 4, 5. So all of them are this one. And once you calculate this value, it's going to give you 0.1750. All right, so we managed to calculate this value, right? So we managed to calculate that value, which is this. Now we move to calculate probability of yes, which is very simple. We have actually just need to calculate how many cases we have, which are 16 of them, and the number of yeses, which we saw was 9 of them. But let's count one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 over 16. So that's the probability of yes. So we managed to calculate these two. Now let's calculate probability of x1. And that's, again, we have to write, sort of like, because we are assuming customer income, years in current job, and education level are independent, we can find that by, sort of like having 3 terms here. So we can say probability of customer income. So let me simplify this. Customer income, years, current job, and education level. So probability of customer income is equal to high multiplied by probability of years in current job equal to low multiplied by the probability of education level equal to masters, right? So now we can calculate these values. The first one, the customer income is going to be 16. We've got 16 data objects, so you have to count the number of high. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, correct. And then we have to do the red term, so let me change the color here. And then years in current job, low. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be 9 over 16. And then let's calculate the blue term. Multiply by, again, we've got 16. And then let's count how many masters we have. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it's 5 over 16. Right? So once you calculate this, you will get this value, right? So we managed to calculate all these three terms, right? So we calculated all these three terms. Let's go back and bring them here, right? So the first one we calculated was 0.1715. So we'll bring that here. 0.1715 multiplied by, it was 9 over 16. 9 over 16, and then we bring back x1, which we just did, 0.0659, right? And once you calculate this, you will get this value, which is the probability of x1 being yes, and it's about 1, which is something we'll discuss. But how about if we decided, wanted to do the probability of no given x1, right? There should be some relationship. This is large, this should be lower. And when we do that, you can actually see it's going to be 0. So for practice, go ahead and actually do this. Now, once you look at these two values, the probability of yes given x1, then you would say, okay, this is probably better to go with yes. So that's how Naive Bayesian actually do this to calculate these probability. All right, so when we were starting to talk about Naive Bayesian, we did say that we need to only have categorical value. If you have numerical value, you have to do either discretization or assume a probability distribution for the data. So we looked at the discretization. Now let's focus on this other way of going about this. So when we want to assume a probability distribution for the data, we basically have to sort of like look at the numerical data, look at its histogram, and say what type of distribution would go better for the data. Let's assume we're going to use Gaussian, like normal distribution. So we assume a Gaussian distribution. We say, okay, we are assuming that customer income follows a normal distribution with mu and sigma, and we estimate mu and sigma as the average and the standard deviation of this column. And also we say, okay, the same thing for years in current job. We assume that it follows a normal distribution. Again, we assume the parameters of mu and sigma as the average of the column and the standard deviation of the column. So once we do this, now we can use the density function of normal distribution to sort of calculate the probability values for one point in time, 4 points. So now let's look at this. Now we want to do this. So we've got numbers here, right? Do you remember it was high or low? Now we went back to before discretized data. So now we have to calculate these terms. So let's start with P equals probability of x1. Now all we need to do is to use the Gaussian this density function to calculate the probability or to calculate the value of that function or the probability of this specific possibility for all of these, right? So we've got to use Gaussian for this one, also the Gaussian formula for this one. Of course, this is discrete, so we can just use the way we know how to do probability for discrete values, which is 5 over 16. And you calculate these values and you get to this number, right? So that's x1, and for x1 given yes, you have to actually update your estimation, right? So we have to assume that if it's because it's given, now we are going to change our estimates for the parameters of the normal distribution. We're only going to use these numbers to calculate the parameters here and here. So we do that, and then we use the new parameters to calculate this probability, and it gives us this value, and of course the probability of yes doesn't change, is 9/16. So once you bring those numbers that we just calculated, you get 1/1.13, and also you get 0. So now looking at these numbers again, you can decide that yes is the best way to go about this. So we do know that there is a probability law that P probability of A given B plus probability of negation of A given B is equal to 1, which makes sense, right? But why in Word, when we calculate the P yes, probability of yes given X plus probability of no given X, where yes, no is actually has this relationship with yes, is the negation of yes, right? It's either yes or no. Why this was not equal to 1? For both our calculations, here it was 1.13, and for the other one also, when we use discretization, it was 1.46 plus 0. So both were larger than 1. Why is this happening? The reason is simple. These are estimation of probability values, and the reason that there is inaccuracy is because we used that assumption, the fact that the independent attributes or the predictors are independent, while we do know that they are not. For example, if you have higher education, your income is going to be higher. Because of those estimation, of course, because this is just a data, this is just an estimation. So once you get to these values, actually what each of these modules that we're going to use are going to adjust these data so they look like probability values. So that's what they're going to do. But anyway, let's sort of like talk about what we just learned. I mean, we learned through an example. We learned that naive Bayesian is a statistical probabilistic classification model. It uses conditional probability to look at the data and come to find classification values. And it uses theory of probability. And one of the greatest things about naive Bayesian is that it actually inherently calculates the probability, which we saw that sometime having that probability can be really meaningful for our decision making over just having a class label as far as our prediction. So let's look at example in R. So we're going to look at the same example as we did for the KNN. So if you haven't watched that KNN video, at least you go back and watch that part that we did R in the previous video. So let's go do the same example. Alright, so again you have to first install some packages and then call them here, and once you do that then you're ready to go. And it may take a few minutes to do this. And you read the data, which is customer loan, and we actually don't need to scale it because it's naive Bayesian. So we can just skip these parts, right? We don't need to scale it. And yeah, we can skip these parts too, right? So now we can go about creating the train set and the test set by using create partition, which gives us indices. And the reason we are using set seed is because we want randomization to be controlled. If you use the same set seed, you're going to get the same randomization. So we do that, and we've got our train set and the test set, and then we say we want to use cross validation by k equal to 2. So I have to run this way, k equal to 2, And then we also set our seed again, because this is also, because it's going to be randomly splitting the data into two parts. So we get the same answers. We can use the same set seeds. So let's run this. Oh, I have to switch some of these codes. So these are mistake. So let's come back here. All right, there we go. Okay, so this is our naive Bayesian fit. We can see that we can get to 75% accuracy. And now let's look at our test set. So we predict for the test set, right? So we predict for the test set, and this is the those prediction. Most of them are yes. And then we create a confusion matrix, and we see that it has some false positives, actually 2 of them. So it makes sense that sensitivity is great, but specificity is low. So for us to sort of like experiment with being able to switch these, or improve one over the other, let's change the normal cutoff point from 0.5, which this function uses. Let's get the probability values, which this is how we would go about. So we get the naive Bayesian probability values for the test sets, right? So these are the probability values. Now let's use a custom cutoff. Instead of 0.5, we use 0.75, which we want to improve for precision. Not that it would be more important, just as the way of experiment to show you that how we can play with this precision and accuracy values. So we run this, and we get our new confusion matrix, and we do see that now we were able to decrease the number of false positives to 1. Of course, our specificity was improved at no cost to sensitivity. So you can see playing with these cutoff points actually may work for us very well. So you might want to actually do that every time. And then lastly, we can also do the ROC. I've gone ahead and done the ROC for the whole data, right? So the ROC is done for the whole data here. So if we run this, let's see, we need to get the probability values first. So we need to run this first. There we go. Now we can do the ROC, and we can see the ROC, and we can also calculate the area under the curve. All right, so let's get back to the slides. Just the summary. In this video, we talked about what is naive Bayesian. We saw how it is fundamentally, how it uses conditional probability to go about finding the classifications and find the classes, and also we saw how we can do this in an example. Until the next video.